are pulling some information from Unit 5. So in Unit 5, we talked about four types of distributions. There were two categories. It was either categorical data represented by proportions, or it was numerical data or quantitative data represented by numbers, by averages. Everything we did in Unit 6 was the proportion stuff. Here in Unit 7, we are going to deal with quantitative average data. So we have already kind of talked about the distribution itself. There are 3 conditions that you check, and we do these normally. We normally check the normal condition, and this is kind of out of order, but normal, we would check random, we check independent. And within these 3 conditions, we say that if it's a normal distribution, all of our normal procedures carry on. Now, the one thing that I will tell you, when you're doing random and independent, these are always the same. No matter what, if you are doing a confidence interval or a hypothesis test, you should always check, is it random, is it independent? Now, that is at least 2 of the 3 things that you have to do. The third one is going to be the one that's slightly different, and that is the normal condition. When we check normal for quantitative data, you are doing kind of one thing, but it could be 3. You are checking, is the sample size, is it bigger than 30? If it's bigger than 30, the central limit theorem tells us it's going to be approximately normal. So it's fine. As long as our sample size is large enough, and I'm going to show you why in a second, why we do that, we say it's normal. There is other possibilities. Sometimes the question will tell you that the population is normally distributed. If they tell you it's normally distributed, we believe them. We say, okay, it's normal. Another thing, which we're going to review today, is you may have to graph the data. 9 times out of 10 on the AP exam, you are not going to have to graph it yourself. They're going to give you the graph, but I am going to remind you how to do a histogram in your calculator because we may have forgotten how to do that. But that is the only difference in conditions that we will check. So we are doing central limit theorem instead of the large counts, which is what we did for proportions. That is solely for proportions. Now, just to remind you, for confidence intervals, we have, when we are doing a confidence interval, the goal overall is to create an interval of values where somewhere in between the lower bound and upper bound is the true population, and in this case, it would be mean or average. Normally, it was proportions. But with this confidence interval, it functions exactly the same way. You are going to come in, you are going to take a statistic. In this case, it's X bar. You are going to have a critical value. And for the first example, we're still going to use Z star. And then you are going to have a standard deviation. The only reason this is referred to as standard deviation and not standard error is because in this formula itself, and it's one of those special cases that we'll kind of talk about, you know the population standard deviation. One of the reasons why we referred to the standard deviation formula as standard error when we were doing proportions was because it was calculated based on a sample. This is one where you know the population standard deviation. So we are going to essentially do the exact same thing. The only change is instead of it being a p hat, we're using an X bar. Instead of it being a square root, p1 minus p all over n, we are doing the standard deviation over the square root of n. So that kind of all changes just based on the fact that we're dealing with means. One of the things I will say, standard deviation formulas, all of them are on your formula chart. You don't have to memorize them. They are there for you. So don't feel like, okay, I need to memorize 17 different formulas. For the most part, you all are going to use your calculator, and that is fine. But sometimes knowing the formula is helpful when it comes to those multiple choice questions. So let's go into example 1. I'm going to use this formula that we have up top. That is what I'm going to use to calculate my interval. I kind of filled in a lot of this for you because this is not the most important one today. And I don't want you to be like, well, she how am I supposed to remember this? You're, for the most part, not going to remember this. A farmer wants to estimate the mean weight of all tomatoes grown on his farm. To do so, he selected a random sample. So here we have a random sample of 4 tomatoes and calculated the mean weight to be 110, assuming the population of all the tomatoes are normally distributed. So they're telling us it's normal. And the standard deviation of his tomatoes in the past has been 40 grams. Use the sample mean to create a 99% confidence interval. Remember, for confidence intervals, they're going to be very straightforward. They are going to tell you, do a 95% confidence interval. That is your obvious point out as to what you should do. For the formula, we need 4 things. We need X bar, which is a sample mean, and it looks like I have a sample mean of 110. We need Z star. That is going to come from our 99% confidence interval. So when we had 99%, the Z star was 2.5758. If you have forgotten, this comes from inverse norm. That's how I got that Z star value. With the standard deviation, we have to know the population standard deviation, which in our case is 40 grams, and we have to know the sample size, which is 4. So all I'm going to do is take these 4 things and plug them into the formula. I did go ahead and check conditions for us. With the 3, 2 of them, again, pretty standard. If I were you, no matter what I'm reading, those are the 2 conditions I am checking. The third one, the normal condition, is the one where it's going to change. You should see a statement saying that the population distribution is normal, therefore the sampling distribution should be normal. And that holds true. If a question tells you that the sample size is, or the population distribution is skewed to the left, that's not the worst case. As long as their sample size is big enough, or in proportions, as long as large counts is met, we still say it's going to eventually be normally distributed. But if it starts out as normal, it's definitely going to end as normal, no matter what sample size you have. So that's why I just said they say it's normal, I believe it's normal. I went ahead, I calculated my interval. One thing I will point out, I named the test. It is a 1 sample Z interval, and the big change for us right now is it's for means and it's not for proportions. So it's number data. And if you're ever unsure and you're like, how do I know it's categorical or it's quantitative, read the question and look at what they are collecting. If they're just trying to get a success, fail, a yes, no, then you just say it's a categorical, because that's all you really got. When it comes to means, they are collecting a number. So they are collecting the weight of these tomato plants or tomatoes. The one addition to our conclusion, because the stem should be exactly the same. We are blank % confident the interval from blank to blank captures whatever. They, in the whole idea of collecting a number, it is going to have a unit. You're measuring how tall someone is. You're measuring how many caffeinated drinks they have in a day. You're measuring how many AP classes they're in. That has a unit attached to it. So whenever you write out these conclusions, make sure that you include the unit within it. When we were doing categorical stuff, it was all a proportion. It was all 20% of people, 30% of people. So you didn't have to specify anything there. The data collected for quantitative stuff is different. So because of that, we include a unit and then we go on. You could also not have it where I do, and then have something that says like the true mean weight in grams of the farmer's tomato plants. But I think that's a little bit hard to remember compared to just like put the unit at the end of the number. So this is a 1 sample Z interval for means. Basic, not too much different from what we normally did for proportions. Where this starts to change and where we get a kind of new formula, but not entirely different, is this whole question hinged on the fact that we know the population standard deviation. That was one of the requirements for me to be able to do sigma over square root of n. Realistically, if you are trying to estimate, and this is kind of what this paragraph says here, but I'm going to kind of summarize it for you. if you are trying to estimate the population mean, you most likely, in most of the cases, are not going to know the population standard deviation. Because if you know the standard deviation, you in turn kind of have to know the mean. So what we do instead, because we don't know the population standard deviation, is we use a different distribution. So this distribution is, we estimate standard deviation from our sample using the sample standard deviation S. So it turns into S over square root of N. However, when we do that, we can no longer use Z star. We are going to use the test statistic and its new distribution. Now, the only reason I show you this and the only reason we kind of look at it is to kind of relate these two things together, one, but there have been many questions in the multiple choice section in years past where they've said, when do you use a one sample Z interval? And the answer is if you know the population standard deviation. That is the only time you would ever do it. They are not going to give you an FRQ where you have to do a Z interval. I would not expect that at all. It's only a question of when do I get to do this? And it's only if you go in and you knew the population standard deviation. If you do that, you can use all of your Z procedures and be perfectly fine. But we have to kind of take on a different distribution because you most likely don't know that information. You're probably not going to have that information. It is very, very rare. So this distribution is called the T distribution. It is basically a Z distribution, but it depends on sample size. The one thing that's going to be kind of confusing for people is it's a family of distributions. So remember, for normal Z distributions, I really harped on the fact that you can memorize these. That was because you cannot memorize the T distributions. They are going to change based on something called a degree of freedom. There is a long kind of explanation we can go into as to what a degree of freedom is. Basically, whenever you have certain things set in stone, I usually use tests as an example. Say you want to make an 80 in the class and you have 3 tests. You get a bad grade on the first one, you get a good grade on the second one, and that kind of locks in what you have to make on the third one to make the 80 in the class that you want. So you kind of lose that freedom of making whatever you want on that last test dependent on the first 2. So whenever we do this, I know it's a big concept. They're not going to really ask you to explain what a degree of freedom is. That's above introductory stats. All you have to know is if I am calculating degree of freedom, it is sample size minus 1. So each of these T distributions, they have a different distribution depending on what their sample size is. They are still going to be unimodal. They're still going to be symmetric. What is going to change is the tails. So the tails on a T distribution are fatter than a standard normal distribution. Basically, that just means they have more area in the tails. They'll often ask you questions of how are a Z distribution and a T distribution different? And it's going to be the fact that they have more area. So I'm going to kind of highlight these in colors so you can kind of see what I'm talking about. This one here, the really tall peaked one that kind of gets flat against the x-axis, this is our standard normal. So this is the one where center is 0, standard deviation is 1. It works out nicely. You can do the 68, 95, 99.7. Then you kind of go to, if I have a T distribution with a small sample size. So this is my sample size of 4, or sample size of 5 because the degree of freedom is 4. What I want you to notice is how high off of the x-axis it sits. So that means there's more area in those tails. And that means the probability, if you were to calculate a p-value, is going to be a lot higher than it would be if it was a standard normal curve. And then you kind of increase your sample size. So we're going to increase it to 25 or 21 because it has a degree of freedom of 20. And you'll notice it starts to get a little bit closer to the standard normal curve. Eventually, as your sample size gets bigger, closer to 30 is kind of the goal, this starts to mimic the standard normal curve. So if you have like a sample size of 1,000 or 500, usually it's going to be very close in terms of what the Z star is or T star is compared to Z. But if your sample size is very small, we can't use it, which is why we say central limit theorem. It has to be bigger than 30 in order for us to say eventually, over time, it's going to be normal. This is just something to kind of go into because they do ask those questions of how are these two distributions the same and different. They are both unimodal, they are both symmetric. It's just when it comes to the standard normal, there's only one. When it comes to the T distribution, there are a family of them depending on sample size, and the T distribution has more area in the tails depending on your sample size. So this is what we are going to use. Now, I want you to not worry too much because it functions exactly the same way. It is a critical value. It is a bounds for a confidence interval. When you go in and you are trying to find the T star values for a certain confidence level, the area is always in the middle. So whenever I say I'm 95% confident, that 95% area is in the middle of my distribution. It is bound by two critical values. Normally we said Z star, negative Z star, positive Z star, but in the case of T distributions, it's negative T, positive T. Now, where this is going to kind of be slightly different. If you want to find these T star values, which you will have to do if you're doing it by hand, we are going to use a function similar to inverse norm. We are going to use second vars number 4, which is inverse T. So it's directly underneath inverse norm. Now, the one thing I am going to point out, there is no tail option. Even if you have one of the newer calculators, the tail option is not going to pop up. So what you have to kind of understand is your calculator, when you enter in an area, it is read from left to right. So if I want a 90% confidence interval, I'm not just typing in 0.90 because really that is not going to get me as far as I need to go. You have to take into consideration the area in the tails. Now, one thing I will kind of remind you, this entire distribution totals up to 100%. So when I have a specific level of confidence, I can use that to kind of figure out what area is left in the tails. So the first example is a confidence interval of 90% with a sample size of 5. So I'm going to go in and we're just going to talk about this a couple times and then do it in an FRQ question. If 90% is in the middle, then that means there's 10% total overall in the tails. But I have 2 of them, so I divide that in half. So I have 5% in the lower half, and I have 5% in the upper half. And this is going to be our positive T star. Now, this is personal preference. You can do 2 things. You can find the negative T star or the positive one. If you want to find the negative T star, all you have to do is put in an area of 0.05. If you want to find the positive one, which is what I normally do, you have to calculate the total area up until that positive T star. So I'm going all the way up to the positive. So that means I'm going to total up the 5% and the 90%, and that is going to be the area that I put into my calculator. Now, I'm going to kind of explain why I do that and why I don't just put in 0.05. I can tell you, it's usually the decimals that will betray you. I have people who see, okay, that's supposed to be 5%, and then they type in 0.5, and that is not the area that you want. Or when you have 2.5%, and then people type in 0.02 or 0.25, it's usually just calculator error. So what I normally find is if you're adding these 2 things together, you have a better chance of not messing up the decimal. But it is personal preference. You could do 0.05. You could put in a degree of freedom of 4. The degree of freedom of 4 is coming from n minus 1, which is 5 minus 1. So that's where my 4 value came from. And then I put this all into my calculator, and I get my t-star. And comparatively to the 90% confidence interval for a z-star, which is 1.6449, it appears to be quite different. And that is because when it's a small sample size, it doesn't really reflect a normal distribution. It has that extra area in the tails. It doesn't quite look like what I need it to look like. Then we kind of look at a sample size of 25. Same idea, same confidence level. We are going to have 2 bounds. If there's 90 in the middle, there's 5% left in each tail. The upper one doesn't really matter. I went ahead and changed the degree of freedom to be 25 minus 1 because of the sample size change, which gave me 24. And this one looks a lot closer to the z-star value. So this is 1.7 compared to 1.64. So it's getting closer to the standard normal curve. Over time, if that sample size gets any bigger, it will start to get closer and closer to 1.6449. I always say, if you, for some reason, are finding that you are trying to pick the right formula or you're trying to do this by hand, if all else fails and you know its means and you know you're supposed to use t-star, you can always try to estimate it with the z-star if you cannot figure it out. Because if it's a large enough sample size, it should be pretty close to that value. So they may kind of grant you some grace and give you some credit for that. Yes, Zoe?
Large enough sample size being over 30?
Over 30, yeah.
If you are 30?
It's 30 or more. It's not going to be, even at 30, exactly 1.6449. It's going to take something bigger than 30. It's just saying at 30, we can say it's normal enough. If you, in the perfect world, you're going to remember to find a t-star using inverse t, but that's worst case scenario. If you don't remember how to do it, you can always substitute it in as just a, most likely you guys are doing this in your calculator anyway, but if you had to, that is where it's coming from. Okay, now, going into this idea that we have to use a t-star, the formula changes slightly. Slightly in just 2 numbers get swapped out. Instead of using z-star, you are going to be using t-star. And instead of using sigma, which is the population standard deviation, you are going to be using S, which is the sample standard deviation. Again, this is more kind of close to what you would expect on a proportions interval. You would use the samples information. This is a 1 sample t interval for means. It is only changed from what we had in our first example by the fact that it is called a t interval and not a z interval. And I know I'm going to get the question, is that something they would take off for if I wrote z instead of t? Yes. You have to correctly identify the type of distribution you are using, and you will never, for means, and I can probably say this with confidence, have to do an FRQ where you know the population standard deviation. It is going to be one where you do not know it, and you are using the t distribution. So let's kind of go through and do an example together. You recently read an article that said averaging 300 minutes will help fend off cancer. Random sample, 45 US adults, asked how many minutes of exercise they get each week. The sample had a mean of 283.2 minutes, standard deviation 22.04 minutes. Construct and interpret a 95% confidence interval to estimate the true population mean. So a lot of the time, what I do is if I have information from the question, I will sometimes just write it into my calculate section because I need these things if I'm going to do it by hand. We are going to talk calculator and by hand today, but they gave me the summary statistics that I got to have. So I'm going to kind of scroll, and in the calculate section itself, I went ahead and just wrote out the 3 things that I know. Now, I am still doing the communicate, the conditions, the calculate, the conclude. So I am going to first, and here's where a big change happens, and it happened in example 1, but I did not point it out now that I'm thinking about it. We are no longer talking about proportions. We are no longer describing a number of successes out of a total sample size. So I have to use mu. Mu is a parameter for means. Mu and x bar are the only symbols you should be using related to the sample and the population for means questions. That is different from p and p hat. Those are strictly for proportions. Now, I have average number of minutes of exercise adults get each week. Then I have to go in and I have to calculate the T star for a 95% confidence interval. Well, if there's 95% in the middle and there's 5% left over, if I divide it into 2 for both tails, my area ends up being 0.975. And this is coming from 0.025 plus 0.95. Again, if you wanted the negative one, it would just be putting in an area of 0.025, and you would get the same exact T-star value, just it would be negative. And it's not the end of the world to get a negative number because this is an interval, so you have plus and minus, so it takes care of itself. But I will say for multiple choice, it tends to be something that they write as the positive value. So you will not see a question where they've written the formula out and the T-star is a negative value. So just keep that in mind. Okay, 2 of the conditions we should always know. Random, independent. Random sample of 45 US adults, which is why my degree of freedom was 44, because I did 45 minus 1. And it is safe to assume that there are at least 450 US adults in the country. Reasonable, works out. Now, this problem, I will say kind of the tier order of how you want to look at these things. The first thing you should always want to check for is sample size. Make sure that if you can do central limit theorem, that is probably best case scenario. And my sample size is 45, which means it's large enough for me to come in and say, okay, it's going to be approximately normal. And if I were doing the Z-star values, a 95% confidence interval is normally 1.96, and my T-star is 2.02 if I rounded that way. So I'm pretty close to the actual Z-star of a standard normal curve, but again, it usually takes a much larger sample size to get there exactly, but 30 is kind of the number where they say eventually, like, we know 30 is going to look as normal as we need it to. So 45 checks out. Those 3 conditions, all you have to check in order to be able to do the calculations. One thing you should always do is name the test. And I say this because most of you are probably going to use your calculator. If you are going the calculator route, you have to name it. Otherwise, they will not give you credit on the AP exam. This is a 1 sample T interval for means. It is always kind of going to be a 1 sample versus 2 sample. Then it's going to be, is it a Z? Is it a T? Is it an interval? Is it a test? And is it means or is it proportions? You will never, ever, ever use T distributions for proportions, ever. There are cases where we can use Z for means. That is if we know the population standard deviation, but you will never use T for proportions, ever. So don't mix those up. Now, I'm just going to take the data that I have and I'm going to plug it in to the formula. I have X bar, I have the T star, and then I have my standard deviation of my sample over the square root of n. Plug it into my calculator, I get a lower bound, I get an upper bound. Now, most of you are not going to use the formula. If you are someone who does, because there are people who like to use it, using the formula itself with the numbers plugged in names the test. So you can technically skip over the step that says one sample t-interval for means by just writing out the formula correctly with numbers filled in. But again, most of you are probably going to jump to your calculator, which is usually my recommendation because it keeps you from having to memorize all of the formulas, even though you should know them, and it saves you some time. So just to kind of show you what that calculator is going to look like, I'm going to open it kind of side by side. You are still going to be in stat tests. So I'm going to go to stat. I'm going to go over to tests. Now, you are going to want to use the one called t-interval. So I'm going to jump all the way down to option 8, t-interval. And there are two options when you open this up. It asks you, do you have data or do you have stats? Data would be like, I have a table of values that I put into L1 and then I want to run this test on that set of data. We have stats. They gave us summary statistics of their sample. So I'm going to go over to stats, and then it's going to ask you, what is your sample mean? What is your sample standard deviation? What is your sample size? What confidence level do you want? You plug that information into the t-interval calculator function, and then you hit calculate. It should give you your confidence interval as well as tell you kind of what you plugged into the calculator. My recommendation, you have to write the name, so one sample t-interval for means, and then I would write everything that the calculator gives you. The reason why I say this, if they can see, okay, their interval is way wrong, I don't know what happened, but they look at what you wrote underneath it, and for some reason, maybe you accidentally typed in 220.4 and not 22.04. That could be something where if the grader has to kind of decide, do I give them the 3 or do I give them the 2? Having a mistake like that may have them be more inclined to just bump you to the 3 rather than bring you down to the 2, because it's not something that you necessarily did incorrectly. It's just you had a calculator error. So sometimes I think it's helpful to have that additional information there just to cover your bases of, I got an interval, it was way off, but it looks like most, because you're probably going to honestly just copy this down directly from your calculator and not even notice that it's 220.4 and not 22.04. But we can see like, oh, they must have put in the wrong standard deviation, and be able to check your calculator work. If I just have an interval and it's entirely wrong, I don't know where it went wrong. So take what you get from your calculator, write it down on your paper. Now, this is stat test 8. I have calculator instructions on the back, the very last sheet of this whole thing. So it's in there if you did not write it down. So we are going to conclude. We are 95% confident the interval from 276.5783 to 289.8217. Notice that I included the word minutes. Captures the true average number of minutes of exercise adults get each week. Another thing to be careful of, because I know we are so kind of used to writing true proportion, it is no longer a true proportion. I'll grab it from there. Thank you. But it is the same conclusion we have been making. Now, the next two things we are going to kind of talk about, kind of switch gears, but not really. The first thing we are going to discuss is sample size. So we are going to still have problems where you have to calculate the sample size given a specific margin of error. The margin of error in the case of these intervals are the t-star times standard deviation over the square root of n. So when I look at the formula that I am currently using, t-star s over square root of n, I run into a bit of an issue, because one of the things that I need in order to be able to calculate a t-star is I have to know the sample size because I need a degree of freedom, which is sample size minus 1. And so if I don't know the sample size, I cannot use a t-distribution. So what ends up happening is we kind of revert back to our previous formula where we know the population standard deviation. So in this case, we cannot use t-star because you need degree of freedom, which is n minus 1. And we don't know what n is. We are trying to guess what sample size we need to meet a specific margin of error. So instead of using this, we kind of revert back to the first formula we used, which was z star times population standard deviation over the square root of n. Now, this is only for if you know the population standard deviation and if you are calculating sample size. But essentially it works exactly the same way as what we did for proportions. Honestly, I think the algebra to get n by itself is a little bit easier for this one than it was for proportions, because you don't have to deal with like fractions within fractions and squares and all of that. Well, you do have squared, but fractions within fractions usually are people's issue, or dividing a fraction by a fraction. So this ends up being a little bit easier. Remember, margin of error is how far off you want to be, because that's what's being added to your statistic, your X bar, and being subtracted. So in this first question, they say, medical researchers want to do a large study to determine the mean cholesterol level of children aged 5 to 10. They want their estimate to be within 1 milligram per deciliter of the true value at a 95% confidence level. Previous studies have shown that the cholesterol level in children varies with a population standard deviation of 5 milligrams per deciliter. What is the minimum number of children the researchers need in their sample to get the estimate that they want? So they tell me margin of error. They want it to be within 1 milligram per deciliter. They tell me confidence level, which is going to help me find Z star. And they tell me the population standard deviation is 5. So the only thing I am missing from my margin of error equation is I need the sample size. So one thing to remember, this is one you can memorize because Z stars are never going to change because there's only one distribution. I have Z star equals 1.96 when I want a 95% confidence interval. So I'm going to take what I know. I know that they want a margin of error of 1. I know that 1.96 is my Z star. I know the sample standard or population standard deviation is 5. I do not know what n is. So I have to come in and I have to solve for n. So basically, I want to get it by itself. The first thing I'm going to do is I'm going to divide both sides by 1.96. And then that is going to get rid of the 1.96 in the front of my fraction. And I get something that looks like this. Now, how you approach this is completely up to you. I personally, if I see a fraction equal to a fraction, I immediately want to come in and I want to cross multiply. So I'm going to cross multiply these two things. Square root of n times 1 and 1.96 times 5. And that's going to give me square root of n is equal to 9.8. And if it's something that I put into my calculator and it's a really long decimal, I don't round it. I leave it alone. But this actually was just 9.8, so I'm going to leave it. The only reason I say that is when this is a multiple choice question, they are usually pretty exact. And sometimes in these types of questions, if you round even the tiniest thing, it gets to be way off. Like it will be hundreds off of what you might need if the sample is large enough. So I usually try to not do any rounding. I know we round the Z star, but I try to avoid it if I can. Anytime you are doing a sample size question, Usually it's going to be reported in whole numbers. And even if it is something where you would normally round down, you always round up. So they would need to look at 97 children. Because I know normally we'd round 96.04 to 96, but we want to round it all the way up to 97. I do get the question of what if it is exactly 96? Then that should work because you have a whole number child and you can stop there. But if you wanted to, if it's an FRQ and you rounded it up to 97, they're not going to mark it wrong. But if it's a multiple choice, you may see exactly 96 as one of them. You would not see 96 and 97 as answer choices if that were the case. They would not both be there. So fret not. Okay, last FRQ, and it's different, but it's not. Way back in Unit 3, so think October, the second week of October. Way back in Unit 3, we talked about experimental design. We mentioned that if I wanted to do an experiment where I can determine cause and effect, there's 3 types of design I could have. I could have completely randomized, I could have blocked, and I could have matched pairs. Now, for the matched pairs design, because that's the one we're going to kind of focus on, you went out and you either had one person do both treatments, or you had 2 people who are very similar and they were paired together and you were comparing their results to each other. So think like identical twins, husband and wife, siblings, or people who play the same instrument in the same grade, things like that. So people who were very, very similar get paired together. And when we did that, we were kind of usually going in with this idea, I want to see how they compare to each other, how they are different from each other. So when we go in and we are doing 2 observations on the same individual or 1 observation on each of 2 similar individuals, we ended up with paired data. Every single pair ended up becoming their own block, meaning we only compared them to each other. That idea that we can go in and calculate a difference between these 2 people, groups, things, whatever we are comparing, that kind of feeds into a t-distribution. When you do this, you kind of have to ask yourself, do I care about the overall group or do I care about the difference between the individuals? And usually if it's something where it's kind of dependent on the person, place, or thing, whatever you're dealing with, it's something where you care about the difference between the individuals, not the group. If I want to go out and I want to compare Richardson High School seniors to Pierce seniors, that is me going out and looking at those 2 groups to see how they compare. But if I want to compare like the senior captain of the cheer team, the senior football captain, all of those things specifically within the high school, I can pair them together. And then I just want to look at the differences between them. But if I'm looking at group versus group, that is a 2 sample set of data. Where people usually mess up with matched pairs, for the most part, it's going to be kind of tricky, but not. They tend to give you all of the data. So just to kind of point out from our example, we are doing identical twins. One was raised in a high income, one was raised in a low income, and they want to compare IQ scores. And so they gave you the high income, they gave you the low income, and then they gave you the calculated difference between the 2. Usually if you open a question and you see that they gave me the calculated differences, this is a 1 sample test. The only thing I care about from this entire sample is how do twin A and twin B, how do they differ from each other? So truthfully, anything here is not useful to you at all. You can completely ignore any of the original values. All we care about, our 1 sample set of data, is the calculated difference. That is the only thing that is important to us. And normally when we do this, it is going to be done, because of that, with a one sample procedure, hypothesis test and interval eventually. And we use the symbol mu of D or mu of diff to kind of denote that we have calculated a difference. The trickier part comes when they give you the two sets of data and you have to find the difference yourself, because it's usually like, oh, well, I need to decide, is this one sample or is this two sample? Ask yourself how they are collecting data. Are they pairing people together? Are they having one person do two things? Those are things that are going to lead you into a paired data FRQ. If they're like, I sampled 500 juniors and 500 seniors, and these are their averages, that is completely two sets of data, separate from each other. But if they're like, I had junior siblings and senior siblings and compared their GPAs to each other, that is being paired with your sibling. So a lot of it comes from how did they collect the data. Now, if you look at a question and they give you a table and there's a row that says difference, it is paired data, no matter what. So use that. But in this case, we have one set of data. It is 8, 5, 9, the 6, 5, 8, 1, 6, negative 1, 10, 1, 2. That's all we care about. So construct and interpret a 95% confidence interval for the true mean difference in IQ scores. So I am going to actually take this one and I'm going to do it solely in the calculator. So I'm not even going to show you how to calculate the T-star. I will kind of tell you, don't think big picture if you are someone who wants to do it by hand. I know these data came from 24 twins, 24 identical twins, separate twins from each other. But I only have 12 pieces of data, 12 calculated differences. So the only thing, if I were doing T-star, make sure that your degree of freedom is 11 and not 23. But I'm not even going to do that because I'm going to talk calculator. We're not going to do it by hand just to save some time. So first conditions, random sample of 12 sets of identical twins. It is also safe to assume we have at least 120 sets of twins in the world, identical twins. Now here is where we go even further back than October. We go all the way back to September, back to Unit 1, back to representing one categorical variable, and we did that using a histogram. So one condition, the last condition that we have to check is the normal. First thing you should always do is see, is my sample size large enough? It's 12. It's not. And then you kind of want to read and be like, okay, did they tell me the population distribution is normal? They did it. It doesn't work. And so this is the point where you have to go in and you have to graph it and you have to see, okay, based on my graph, is it unimodal? Is it symmetric? Is there any strong skew? Are there any outliers? If there's not, we're just going to keep moving forward. Now, in this particular question, my recommendation, because you could do a dot plot, you could do a stem plot, you can do a variety of things. I'm going to show you how you can get a histogram in your calculator. Some of you may remember how to do that. Some of you may not. So in my calculator, and I would follow along if I were you, because we will use this to actually run the test in a second. I'm going to go to Stat. I'm going to go to Edit. And then I'm going to type in all 12 of my data values. Let's see. There we go. Let's do this. I don't know how to get that from. Let's see if I can do this side by side and it works out. There we go. 1 second. Let me disconnect so I can tell calculator where I'm getting these specific numbers from. If you hit the trace button and then you start moving left, right, it'll tell you the lower bound, the upper bound, and the count in the graph on your calculator. So you can use that if you have to. The only time I would imagine you actually have to graph it yourself may be a multiple choice question, but the data would not be very large. If you find on the AP exam that you're typing in like 50 values and you've been putting numbers into L1 for 5 minutes, you're probably doing something wrong. So they try their best to avoid having you type in values because that usually invites a lot of error in terms of like, oh, you should have typed 10 and you typed 100, or you should have typed 10 and you typed 1. And that is not what they want to happen. So they use a lot of summary statistics, and they use a lot of, we've graphed this for you, tell me what this graph is, tell me what it represents, what are you looking for? Now, to kind of finish this up, with the name of the test, I'm going to have a 1 sample t interval for paired data. The big change here, if it is a paired data question, we no longer just say for means, we note that it is for paired data. It is assumed anytime you are referencing paired data that it is means, because you don't pair people together for a categorical question. Now, I am going to use the calculator to find my interval. So what I'm gonna do, I already have my data in my calculator. I put it into L1, I have it in my list. So if you have data instead of stats, you are going to want to go and you're gonna want to go to stat, tests, 8, and then you want to be on the data side of things. And it should ask you, what list do you want us to look at? Frequency, keep it at 1. What confidence level do you want? And then you hit calculate. And you should get your confidence interval from the list of data that is in your calculator. One of the reasons, and I'm gonna switch back over so you can kind of copy that down, you don't have to write the steps. I wrote the steps for the sake of you knowing what I did. It is not a requirement. You don't have to do it on your tests. You don't have to do it on the AP exam, but that is what I put into my calculator. Or you could use the formula. One of the requirements for using the formula is you have to know the sample mean and the sample standard deviation. And in order for you to do that, you have to put your data in your calculator and use one of our stats to find the mean and find the standard deviation, which at that point, if your data is in your calculator, then you might as well just use the calculator function to run the test. So yes, it's still possible to do this by hand and it will work, but it's going to require more work from you just because you have to still put your data in the calculator. You still have to run one of our stats. You still have to get X bar and SX. And then after you know that, you go in and you calculate the interval. So usually my recommendation, if you have data, I tend to not even attempt it by hand. Not that it's wrong or it's bad, but it just requires a little bit more work. If they give you a table and then they say the summary of the values is the X bar is this and the SX is this, then sure, use what they give you. But if it's only a table and you have to calculate it yourself, I would just use stat test 8. We are no longer using the proportion ones. We are only using means questions for this test. So yes, eventually when we start like official AP prep, we will start mixing these together and practicing like identifying when to do each one. But I'm not gonna pull anything on your test where I'm like, oh, I'm just gonna throw a proportions question on there and see if they notice. This test is going to solely be for means. So keep that in mind. You should only be doing T